video, we're going to learn the definition of the derivative of a function at a point. And that derivative is going to be the instantaneous velocity or instantaneous rate of change at that point, or the slope of the tangent line. So let's start with the slope of the tangent line, since we've never actually defined it. We've never defined what a tangent line is. We've talked about it, and we've looked for it, and now we're going to define it. Suppose we have the graph of a function, y equals f of x, and we have a point with x-coordinate a and y-coordinate f of a, and we'd like that line that just hits the graph at that one point. Remember, to get the equation of a line, we need two bits of information. We either need 2 points on the line, or we need a point and the slope. So what we do to get the slope of this line, since we don't have another point, is we take another point on the curve, call it Q. It has x-coordinate and y-coordinate, x comma f of x. And we take the slope of the secant line that joins those 2 points on the curve. We call that MPQ, right? It's the change in y over the change in x. That's the slope of that secant line. And then we move x a little bit closer to a, and we take another point a little bit closer, take the slope of that secant line. We take another point to x is a little closer to a, take the slope of that secant line, and we keep taking points whose x-coordinates are closer and closer to a, and we get secant lines whose slopes are approaching, hopefully, the slope of the line we're looking for, the tangent line. So now that we know how to calculate limits, we can use limits to find the slope of that line. So here's the final definition of a tangent line. The tangent line to the curve y equals f of x at the point a comma f of a is defined to be the line through that point whose slope is the limit as x approaches a of f of x minus f of a over x minus a. So it's the limit as the x-coordinates approach a of the slopes of the secant lines, as long as that limit exists. So if that limit doesn't exist, right, then there is no slope. If the limit is getting arbitrarily large, and sometimes we say it's going off to infinity, it could mean that we have a vertical tangent line. Vertical tangent lines don't have a slope. All right, let's look at an example. So in this example, we're going to find an equation of the tangent line to the curve y equals x to the third at the point 2, 8. We've got a point, all we need is the slope. So we set up the limit. So the slope of our line is going to be the limit as x approaches 2 of f of x minus f of 2 over x minus 2. So change in y over change in x. F of x is x to the third, and f of 2 is 8. So now, remember how we do this. We use limit laws, but we can't just plug in 2, right? Because if we plug in 2, we get a 0 in the denominator and a 0 in the numerator. That's called an indeterminate form. We don't know if it exists. We don't know if it's a number, but we have to do something to find out. So usually when it's a rational function like this, factoring works. And of course, this one does factor. X minus 2 times x squared plus 2x plus 4 in the numerator. And so we can cancel. And this limit is equal to the limit as x approaches 2 of x squared plus 2x plus 4. Now, remember, those functions aren't equal because they don't have the same domain, but we're just taking the limit. So the limits are equal. And that's why we have to keep writing lim x approaches 2 in each line. Because if we didn't write lim, we would be saying something that's completely false. So now we have a polynomial, and we know we can just use direct substitution. So this limit is 2 squared plus 2 times 2 plus 4, which is 12. Great, we've got our slope, we've got the point, and we can write down the equation. So it's y minus the y coordinate of the point is equal to the slope times x minus the x coordinate of our point. That's the point slope form of the equation of the line. If we wanted it in slope intercept form, we would just distribute that 12 on the right side, add 8 to both sides, and in slope intercept form, it's y equals 12x minus 16. All right, so what does this look like? So the graph of y equals x to the third looks like that, and the point 28 is about there, and the tangent line looks like it's about there. So that slope looks pretty steep. Looks like it could have slope 12. And our equation is y equals 12x minus 16. So there's another alternate form of the definition of the slope of the tangent line. So let's look at the alternate definition. Sometimes this definition is more useful in certain situations. So let's start again with a picture of a curve and a point P. The coordinates are A, f of A. So now when we take another point on that curve, Q, instead of calling it x comma f of x, let's say the x coordinate is a distance of h away from A. And then the x coordinate we can say is A plus h. Instead of calling it x, we'll call it A plus a little bit. And then the y coordinate is f of A plus h instead of f of x. Okay, and then we've got the secant line, and the slope of that secant line is f of A plus h minus f of A, that's the change in y, over the change in x. Well, the change in x is just h, that distance between A and A plus h. Then we want to take a point closer, an x-coordinate closer to A, and so h is getting a little bit smaller when we do that. So the next point is has x-coordinate A plus h, but h is a little bit smaller. And then if we keep going, get a little bit closer, h is getting smaller. And when we get to the tangent line, h, that distance is 0. So that means we can write the limit a little bit differently. So the slope of the tangent line, if we use this alternate notation, is the limit as h approaches 0 of f of A plus h minus f of A all over h. So it's the change in y over the change in x, but remember the change in x is just that little distance h. All right, let's do an example using this notation. So here we're going to find an equation of the tangent line to y equals square root of x at the point 1, 1. Let's write down the limit that we're going to compute. So it's the limit as h approaches 0 of f of A plus h, and in this case A is 1, minus f of 1 over h. So that's f of A plus h minus f of A all over h. All right, so f is the square root function, so let's write this as the limit as h approaches 0 of the square root of 1 plus h minus the square root of 1 over h. All right, we can simplify it a little bit. The square root of 1 is just 1, so square root of 1 plus h minus 1 over h. All right, so we can't plug in h equals 0 because once again, we get a 0 in the denominator and a 0 in the numerator. We got to do something algebraically. The trick here when we have a radical function like this is to multiply and divide by the radical conjugate. So the conjugate of that numerator is the square root of 1 plus h plus 1 instead of minus 1. And then we also have to divide by that. So when you multiply and divide by the same thing, you're not changing your number. All right, so now we multiply across on the top. Notice we have a minus b times a plus b, and we always get a difference of squares, a squared minus b squared. So we get the limit as h approaches 0 of the square root of 1 plus h squared which is just 1 plus h, minus 1 squared, which is 1. And then in the denominator, it looks more complicated, but we'll just leave it factored. It's h times that conjugate. All right, notice what happens. In the numerator, 1 plus h minus 1 simplifies, and we just get h in the top. And in the bottom, because we left it factored, so never multiply things out, always leave things factored. So because we left it factored, we can see we can cancel those h's. So what we're left with is the limit as h approaches 0 of 1 over 1 plus h plus 1. And now we can plug in h equals 0 without having any issues. When we do that, we get 1 over square root of 1 plus 0 plus 1, or just 1/2. So now we've got our slope, 1/2, and we've got the point, 1, 1, so we can write down the equation of the tangent line. In point-slope form, it's y minus 1 is equal to the slope times x minus 1. If we want to put it in slope-intercept form, it's y equals 1/2 x plus 1/2. So that's the definition of the tangent line. And so that's the definition we're going to use also for instantaneous velocity and the derivative of a function at a point. And I'll see you in the next video.